Hello everyone, welcome back to the channel. Today we are taking on a massive system design challenge. We are going to explore what it takes to design a chat application like WhatsApp or Facebook Messenger with over 200 with over 2.5 billion active users and 100 billion messages exchanged every day. Facebook Messenger is one of the world's most popular messaging apps. But what does it takes to design such a scalable platform and scalable system? So stick around as we dive into high-level design of real-time messaging application. So first, let's just make a quick introduction. So imagine creating an application capable of connecting billions of people across the globe, delivering messages, images, and videos instantly. It's a massive undertaking. Okay, so today we will discuss the key components, architecture, and the challenges of designing a chat system like Facebook Messenger. We will cover aspects like scalability, low latency, reliable message delivery, and support for group chat. So, without further ado, let's dive into our requirements gathering. So, in your system design interview, when your interviewer asks you about to design a specific system, the first thing you need to know what is this system. So right now we made a quick introduction of what a Facebook Messenger is. Hopefully, most of you knows what is a Messenger is, but this step is huge. It's big. The second thing is to start in gathering the functional requirement and non-functional requirements, and I would say this is the most important step in any system design interview. So, in the function requirement, we need like a real-time messaging. Also, we need to support online, offline status. We need to have a message delivery a status like read receipts. We need to add push notifications. We need to add groups for chat groups. Yeah, let's say this is enough for now. And in the non-functional requirement, we expect our system to be scalable, the latency should be low, and our system should be highly available and secure. Next, we need to talk about the capacity estimation. So let's assume that we have 500 million daily active users. A peak time will be 50 million users connected at the same time, assuming the message is around 1 kilobyte, and we have about 5 billion message every day. So we could have daily about storage 5 terabyte. With this lead us to annual 1.8 petabytes. So when we nail this first section, which the functional requirements and the non-functional requirements, and we go through our capacity estimation, I guess we have a clear idea of our system and how our system will look like. So let's start first with the client. Okay. Okay, we have the client now. And the client will send the request through like a load balancer. But it's important to know what the type or what the client like. Let's say that we have client one and let's say client A. And the client A, and we have as well client B, and both of them want to chat with each other. So they will send the requests or they will be connected with a load balancer. But they will be connected with a load balancer using WebSockets, and it's really important to say that they are be using a WebSocket because WebSocket is bi-directional communication, and unlike it's way more different than the normal HTTP or like REST response, which is response requests. Basically, WebSockets allow for bi-directional communication. So we have that when a client A sends a request to the load balancer or like to, let's say that to the server will have the ability to send the message to the client because we need our servers to have the ability to send the messages and notifications without our clients requesting it every 1 or 2 seconds, So it's important to say that the client A and client B will be connected with a load balancer using a WebSocket. And then we will have our own chat servers. So let's just say that we have our chat servers. Um, let's copy this one. And let's say we have chat server 1. Let's make it. And chat server 2. Okay. As well, the load balancer will be connected with them using WebSocket as well. Okay. 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 So right now we have our the load balancer will be connected with the chat servers. The chat servers should has like as well, because when the client sends the request to the load balancer, and it will be connected with the load balancer, and the load balancer will be connected with the chat server, we need to store that, because we want to make sure that if client A is connected with chat server 1, we need to store that, so whenever client A needs to connect again or send any request again, it will be directed directly to chat server 1 and not chat server 2, so we will have no cache missing. So we can do this by have like a Redis cache, which will oh, this is too big. Like a Redis cache will be like user connection cache. Let's put it here. I guess in this way is better. Yeah. So we have our own user connection cache. Okay, so as well, also we need to have like a notification servers service when we ever want to send notifications to our users. So let's has like a notification servers. We can use like third party notification service, and we make this small, and let's make it here. Yeah. Okay. So our system looks good for now. So what will happen then? Then we need to see how we will deal with the messages. So whenever the client A sends a message, it will go to the balancer, it will go to the chat server. It should be sent to a message storage service, and the message storage service will should direct the message to server 2. However, I guess it's a good idea to use a message queue to handle that. So if the message was failed to be sent, it will be stored in the message queue to be retried again. So let's say that we will have like a message queue. That will be connected with both of the client. Okay, and the message queue will and the I guess the message store service will pull. Oh no, let's make it different. Will pull the request from the message queue. So we have message storage service. And the message storage service, it has its own DBs. It will have like message DB. We can use, I guess, NoSQL for that, and we will discuss this in a bit. Also, because we want to serve chat applications, let's have like we need to have like a group chat service. And this group service will be heads like to be connected as well with the DB. Let's have the DB with round like a group DB. I guess I'm not missing anything. Yeah, yeah, I guess I'm missing something. Because our messages might have media, so we could have media service, and this media service is storing like records, like voice chats and stuff. And this media service will store everything in a blob storage like AWS S3, and the media service. And I guess it will be a good idea to cache everything. Let's just put this things like that. To cache everything in a CDN. Let me just pull it in. To cache everything in a CDN, and the CDN will be cache all the static content and send them back to client 1, client A, and as well as to client B. Okay. Okay, so let's try to discuss this um, system in details. Okay, so first we have the chat servers. A chat service is responsible for managing user connections, and it's responsible again. Oh, sorry, Miro have restarted. So the chat servers. Let's start with them at first. So the chat servers are responsible for user connections and facilitating real-time message exchange between clients. They handle establishing WebSocket connections, routing messages, and maintaining session persistence. We have the load balancer. The load balancer distributes incoming traffic across multiple chat servers. Instance to ensure efficient handling. It maintains sticky sessions for ensuring user connections to the same server they were previously connected to. Alternatively, service discovery mechanism can be used to guide users to the correct server instance. We have user connection cache, this one. This component keeps track of each user's active connections details, such as which chat servers they are connected to and their last active status. And an in-memory store like Redis is used here to quickly look up and update update connection details, helping in tracking online offline status and routing messages appropriately or appropri- appropriately. Okay, sometimes I lose my pronunciation. Appropriately. We have the notification service here. The notification service handles push notifications for users who are offline or not actively using the app. It integrates with external push notifications providers like Firebase Cloud Messaging or Apple Push Notification Service to deliver new messages alerts. We have the message queue here. The message queue is a distributed high throughput systems like Kafka or RabbitMQ is used as a message queue. It temporarily stores messages, decoupling the real-time chat processing from message storage, thereby improving scalability and reducing latency. Um, Number 6, we have message storage service. This one. So message storage service, this service consumes messages from the message queue, and messages are durable and yeah, sorry. This service consumes messages from the message queue and persists them to the message DB for future retrieval. The storage service ensures that messages are durable and can be retrieved for chat history purpose. Number 7, we have the message DB, and this is an important one to talk about. And this database stores all chat messages reliably using distributed NoSQL database like Cassandra, ensuring that we achieve high write throughput essentially for real-time messaging system. It also allows efficient retrieval for chat history and supports scalability. Um, let's talk about the media service and the blob storage. So media service handling the uploading of multimedia content such as images, videos, and audio files. Files are uploaded directly to blob storage like AWS S3 for long-term storage, while a CDN is used to ensure media delivery is fast and geographically optimized. Um, I guess next we have a group service. The group service. Um, the group service manages group chat functionalities such as group creations, membership management, and messages fan out to all members. When a group message is sent, the service retrieves the list of members, and the chat server sends the messages to each connected user and or triggers notifications for offline users. And lastly, I guess we have the content delivery network. This component is crucial for delivering multimedia content efficiently and fast. When a user shares media, the media is uploaded to a CDM to ensure that users accessing it experience a low latency regardless of their geographic locations. I guess we can talk about database schema, but I guess I will push this at the end. I guess I don't know if I will have like energy to talk about it or not, because I want to focus on detailed components breakdown, specifically in on the service that we talked about. And let's just have a quiet look to the chat servers and the load balancer, because it's a quite important thing to talk about. The chat servers, as we said, that it manages users connection and handles message routing and maintain sessions persistent. The load balancer ensures that the user requests are distributed evenly across available services. We use sticky sessions as we said before, so each user reconnects to the same chat server for constant communication. Protocols like WebSockets are ideal for persistent two-way communication, allowing efficient delivery of the messaging. So, if you want to talk about as well the user connection of the cache, we use a fast in-memory database like Redis to manage the user connection details. The user connection cache tracks which server each user is connected to, enabling us to effectively routing incoming messages and manage online offline status. We have the notification service. The notification service is crucial for users who are offline. Messages meant for offline users are sent to the message queue, then processed by the notification service, which integrates with Firebase Cloud Messaging or Apple Push Notifications service. This way, users receive instant push notifications for missed messages. We have the message queues and the storage. So to handle the load of real time, we use message queues, and I guess we use Kafka for that. The message queue decouples real time chat handling from message storage, ensuring that servers aren't overwhelming during a peak loads. And the message storage, like consumers message from the queue and stores them in MessageDB for reliable retrieval. We could use Cassandra for high write throughput and scalability. In the media service and the CDN, handling multimedia is always a challenge in a chat application. The media service allows the users to upload images, videos, and audios. Files are uploaded to a CDN or like content delivery network for quick access and for a long-term storage. They saved in a blob storage like AWS S3. This setup helps reduce latency and ensure efficient media delivery. And lastly, the group service. Again, the group service conversations are handled by the group service. It manages group creations, membership, and message fan out. When a user sends a message to a group, a chat server queries the group service and get the list of members, and then sends the message to each member individually depending on their connection status. We could actually look about a way to solve this or to fix this one by using like a pub-sub architecture, which means that the users will subscribe to like a pub-sub channel, and the group service will be the producer. When the group service send the message, it will be sent to through the producer. And we need to talk about why we're using WebSockets a lot, because we use a WebSocket here, we use a WebSocket there. Um, so we opted for WebSockets over HTTP polling and long polling due to the following advantages. First, the persistent connections. WebSockets providing a persistent two-way communication connection between clients and servers. This reduces overheads as compared to polling, where repeated HTTP requests consume bandwidth and resources. Also, low latency, because with WebSockets, data can be pushed from server to the client immediately, enabling real-time updates with very low latency. Number three, efficiency. Unlike long polling, which keeps connections open until the event happens, WebSockets keep the connection alive in a way that's more efficient for handling millions of concurrent connections. If you want to talk about the message delivery and status indicator, how the message sent will be. So let's say that we have user A, and user A wants to send the message. So the user A will send the message, and it travels to the load balancers. It go to the chat server through the WebSockets, which is connected to, which then pushes it to the message queue for the storage, and then when it goes once it hits the message queue, or once it hits the message storage server, it will update it will has a status of sent. Okay. The message delivery status will be if user B is online. Basically, the message service will send the request to the message queue, and my chat service get the message from the message queue, or we can just send it directly. However, if user B is online, the server should or will forward the message to user B via their WebSocket connection, and user A receives a delivery status. If the message read, like once a user B reads the message or open the message, the client sends read acknowledgement, which propagates back to user A. If you want to talk about the group messaging workflow, let me just clear everything, because it will be easier for me and for you guys to understand everything when we just try to clear everything. So if you want to talk about the group messaging, so handling group messaging can be challenging due to high fan out workload. For instance, in a group of members of 500 million, every message must be delivered to all members individually, and to make it this efficient, the chat server first queries the group service. Okay, so it will just queries the group service for member details. If it uses a user connection cache to determine which members are online, and delivers the message accordingly. Offline users receive push notifications, while the message is stored in message DB for later retriever. In terms of the storage handling bottlenecks, like with billions of messages and multiple content, storage is a critical challenge. So we can use sharding, like we could shard user and message data to distribute the load across multiple servers, which helps in scaling horizontally. And also we need to archive older messages, like we store recent messages in primary storage for quick access, while older messages are moved to a cold storage like Amazon, Glacier, to optimize cost. Also, we could compromise and decouplation, like compromise large files and avoid duplicate media storage. In conclusion, I guess that's it. So, designing a scalable chat application like Facebook Messenger involves managing millions of concurrent connections, ensuring low latency, and providing high availability. all while supporting group chats and media sharing. The components we discussed, from WebSockets to message queues and content delivery network, are essential to build a robust and reliable systems. I hope you found this video helpful in understanding the complexities of chat system design. If you like the content of this video, please like, subscribe, and hit the notification bell so you'll never miss a video. And see you guys in future videos.